Okay. So today we have Marta Reboiro, and she will talk about the famous Swanson model, but beyond the PT-symmetric phase. Yeah. So whenever you're ready, the screen is yours, Marta.
Okay, thank you very much. Well, hello to everybody. First of all, I want to thank the organizer to let us share the work we are doing here at La Plata, the University of La Plata, with Romina Ramirez and Viviana Fernandez, who is a PhD student, and this work is part of his PhD thesis. And we shall begin by giving a brief review of some related previous work we have done and how we related some time ago non-standard Hopf algebra with the Swanson model. And then we shall we shall construct regions in the parameter model space of the Swanson model and try to provide the generalized eigenfunction and the related spectrum for each of them. Well, some time ago, we started with Osvaldo Chivitarese and I started the collaboration with colleagues of the University of Burgos in Spain, particularly Ángel Ballesteros and Francisco Ranz, and they were working on that moment on a non-standard Q-deformation relation of the harmonic oscillator. Basically, this is the algebra of the usual oscillator, and they studied this Hopf algebra with these generators, and clearly this algebra, when lambda goes to 0, recovers the usual Weil algebra. So at that moment, we were not aware of non-Hermitian dynamics. So we just look at this problem from a different point of view. We wanted to see if this deformation of the algebra introduces true interactions. Sorry? Sorry? Somebody?
No, somebody just accidentally put on the microphone.
Okay. We wanted to know if this deformation of the algebra induces true interactions. So we propose boson mappings to deal with this type of structure, and we have two options, an exponential mapping and a logarithmic mapping. Obviously, both mappings preserve the original algebra, and then we introduce, in analogy with a standard oscillator, the operators P and X in terms of the new A plus minus, and related them to the original ones, and we end up in each of the mappings with expression of these types. For the exponential mappings, we have a series in terms of A and its adjoint, and for the mapping, logarithmic mapping, in terms of A daga, simply. So we say, well, we shall look at this Hamiltonian. The most, the first we thought was P squared over 2m, and then with the A of this series expansion, we end up with this type of Hamiltonians. At this time, we say, really, the deformation introduce an interaction in the system. To deal with this structure, we say, well, we shall take power of lambda order 3, and both in the boson exponential mapping and in the logarithmic mapping, we truncated the series expansion, and we end up for the expansional mapping, for instance, with this type of Hamiltonian. Clearly, it is a non-Hermitian Hamiltonian, but we try to cast this Hamiltonian into a kinetic term plus a potential. And we succeed in doing this through this local gauge transformation. At that point in time, we were not interested in the dynamic of the problem, but we wanted to prove our answer that the deformation really induce interactions. And we were pretty happy when we found that with this local gauge transformation, we can map this Hamiltonian into a kinetic term and a potential in powers of Q up to 4. The same structure, we found the same structure for the logarithmic mapping. And then we say, well, we shall modify a little the original Hamiltonian and let us introduce a parameter eta and parameter zeta. The structure of the mapping Hamiltonian is a little more complicated, but in the end, after making the same assumptions, we end up with Hamiltonians that can be casted also as a kinetic term and a potential in powers of Q up to the power 4. And the same for the logarithm mapping. This is only algebra. And what is interesting is that by adjusting the constants of the model, the parameters of model zeta, eta, and lambda, we can reproduce pretty well the structure of the good Saxon of a good Saxon potential or the post-Taylor potential. Except for the case of the first Hamiltonian with exponential mapping, the other mappings reproduce pretty well the shape of this type of potentials. Well, this was what we wanted to prove at that time. Though we know we have ended up with a non-Hermitian Hamiltonian, due to the application of this local gauge transformation, we end up with a potential in powers of Q, and we were pretty happy at that time with these results. Sometime more recently in time, we began to collaborate with Romina Ramirez, and we look at the Hamiltonian of this Hamiltonian again, but in the spirit of non-Hermitian dynamics. We say, well, we have this Hamiltonian, it comes from a non-Hermitian algebra in the sense that A plus and A minus are not Hermitian conjugates. We have this pretty boson realization of this algebra. Let us take delta equal 1, beta equal 0, so we have what we have done before. And we map this Hamiltonian again in terms of the usual operators for the harmonic oscillator. And we end up also with this expansion in terms of the oscillator, the boson oscillator operator, the boson of the oscillator, harmonic oscillator. And we say, well, let us take order lambda 3, and let us separate this Hamiltonian in two portions. In one we have the quadratic terms of the Hamiltonian, and in the other, we let the rest of the Hamiltonian. Let us concentrate on what happens on the quadratic terms. We found that if we make a similarity transformations given by these operators in terms of x and p, with this particularly choosing of constants a0 and a1, in terms of the original coupling constant zeta, lambda, and eta, we end up with a Hamiltonian. We have the structure of the Swanson model. So we realize that the formation of this algebra has as its simplest realization the Swanson Hamiltonian. But here is a list of most important papers on Swanson Hamiltonian. I apologize in advance because surely we have missed some of them. And we'll say, well, if we have a Swanson Hamiltonian, clearly we can construct an Hermitian Hamiltonian H related to the Swanson Hamiltonian also through this. Sorry?
Again, just somebody switched on the microphone. Just keep going.
To a Hermitian Hamiltonian, which I call H. This is the similarity transformation. I think most people in the audience is familiar with this part of the work. And we map the Swanson Hamiltonian to the Hamiltonian of the squeeze oscillator. This is the Hamiltonian of squeezing in the boson degrees of freedom. I shall show why we say that this is the Hamiltonian of squeezing. Well, clearly, we can construct for the Hamiltonian the usual Bogoliubov transformation associated with the Swanson model, and we can construct the eigenvalues and eigenfunctions for this PT-symmetry phase. The ground state can be constructed in this way, and this ground state is a squeeze state of the system. What do I mean? Well, this will be clear in a moment. The first thing we can see is in terms of the parameters of the model, in what region we can map our Hamiltonian to an Hermitian one. The region plot in is the region where we have PT phase symmetry. In this region, we can map the Swanson Hamiltonian to an Hermitian one. In this region, we have a similarity transformation between H and the Hermitian Hamiltonian, and we have a symmetry operator between H and the adjoint H dagger. The symmetry operator is constructed with the aid of the operators of the similar transformation from H to the Hermitian one. And if the metric is positive, if this operator is defined positive, we can define a metric with the A of it, and we can construct a B-orthogonality basis. I think everyone is pretty familiar with this. H has if this is the eigenstate of H, the eigenstate of H of the adjoint of H are related to this one through the operator U, and we have this condition for the orthogonality. So we introduce a new inner product. The inner product between phi and fc will be defined in this way. This is equivalent to this condition of the orthogonality, and we can introduce an identity. What thing that is important is that if we want to compute mean values of observables, we not only need the inner product, but we have to map our operators to the new space if we are to make things consistently. Then we shall define the mean value of an operator O through this prescription, and by doing so, we now can speak of time evolution by applying the operator E, the evolution operator on the states of the right, and we shall take mean values of time, remembering these prescriptions, and we end up with this type of structure with time evolution. Why I said that the Hermitian Hamiltonian, similar to the Swanson Hamiltonian, is the Hamiltonian of the quiz boson system, is because if I compute the standard deviation for the operator X and P for the ground state of the system, what I found is that the product of these two standard deviations gives the minimum value of the uncertainty principle, and that the uncertainty of P is always lower than 1, and the uncertainty of Q is always lower than 1. Then we said, well, let us look at the evolution of a gaseous state. A gaseous state is a state constructed in this way. For the harmonic oscillator, this goes clearly to the coherent state of the bosons. When this is not a harmonic oscillator, this is more complicated, but we can construct the evolution of this state, and we saw that as a function of time, the evolution was periodic. That was clear because the spectrum was real, and at each time of time, the uncertainty remains constant to the minimum value, while the P operator is squeezed and the X operator is not a squeeze. That is, the squeezing of P is on the anti-squeezing on X. And if we plot the trajectory in the phase space, we see that we obtain a closed curve. We work a little bit and we construct the Wigner functions, and we see the Wigner functions show the periodicity we have in this figure, and they reproduce the pattern of squeezing at each time of the evolution. So we came back to the Hamiltonian. We have the quadratic term and the rest, and perform another similarity transformation. After overcome some algebra, we end up with a harmonic Hermitian Hamiltonian in powers of x and p. And when we study the time evolution of this Hamiltonian, we observe that the system continue to be squeezed in time, though the the trajectory in phase space was bounded by it was not closed. That is, and we can understand this because we have other potentials than x squared and p squared in the Hamiltonian. So we learned that the non-standard deformation induce an interaction, and that the quadratic part of the interaction is related to the Swanson model. And the Swanson model in the PT-symmetry phase to the squeezing Hamiltonian of a system of bosons. When we were here, we wanted to know what happened with the other portion of the spectrum. We know that it was complex, but we think, well, we shall, before this, we shall try to understand what happens in systems with finite dimension. So we spent some time studying a system with finite dimension, non-Hermitian system, but where the metric was not, where the symmetric operator between H and its adjoint were not defined positive. So we work in the framework of Crane space, and then we say, well, what happens with Crane space in system with a finite dimension? And we learned that it was not so trivial to treat the system with infinite dimension in the framework of Crane space. There are a lot of conditions that the system has to fulfill in order to apply the formalisms of Crane spaces. So we come again to the Swanson model, and we make a parameter diagram in the model space of in the parameter model space of the system, and we say, well, what do we know and what do we not know? And we say, well, the original Hamiltonian is the Hamiltonian of the squeezing, and we know that it has analytic solution when in this region we can map these operators to an S1, an SU11 group, and for these values we have analytic solutions of the Hamiltonian. Now, Swanson Hamiltonian, alpha different from beta. Well, in this regime, omega squared minus 4 times alpha times beta, here should be greater than 0. Here should be greater than 0. Sorry, this is in print. We have the PT-symmetry phase. We can map the Hamiltonian to this, and we know how to work, and we know how to make things. A lot of people work, have contribute to this. And to our knowledge, there was less things said on the other regime. So we try to put this in a context where we can have a few parameters which tell us what happened. Then we come again to the oscillator, the momentum and coordinate operators in terms of for the harmonic oscillator, and we write the Swanson Hamiltonian in this way. The first thing we have to notice is that the adjoint of H is simply exchange alpha and beta. And then we say, well, let us introduce this particularly choice of operators. By choosing P in this way, we rewritten the original Hamiltonian as a Hamiltonian similar to that of the harmonic oscillator, similar in shape or form. And we have introduced the effective parameter M, let us say an effective mass, and the parameter K, let us say an effective vectoring parameter, and we put them in terms of omega, alpha, and beta. We have defined omega as usual as the square root of omega squared minus 4 times alpha times beta. And depending on the value of alpha and beta, this energy can take real or imaginary values. And our effective mass can take real, it's always real, but can take positive or negative values. So we plot.
Where does, sorry to interrupt, where did the B0 come from?
It's a dimensional parameter in terms of, in unit of length also. It had to do with the system you want to modulate, but it was only for a dimensional question that we introduced the beta zero, B0. Well, we plot omega square and we plot M, and we find that omega square can take negative and positive value, but it is continuous function. Omega is always different from zero in our assumption. And M can take positive values or negative values, but there is a discontinuity along this plane. So we end up with 4 regions. A region where M and omega square is positive, a region where M is positive and omega square is negative, a region where M is negative and omega square positive, and the other region where M is negative and omega square is negative. Then at this time, when we have this sketch, we think, well, this should correspond or should be similar to a parabolic barrier. While this is more strange, a parabolic barrier with negative mass. And in this region, we should have a harmonic oscillator with effective negative mass. We define this parameter, which is basically proportional to the square root of n times omega, and we look at the phase of this parameter. And we look at the phase also of omega. We found that in region 1 and 3, gamma can take a value 0 and p over 2, and region 2 and 4, gamma will have by take values plus minus p over 4, and in region 1 and 3, omega will be real, while in ratios 2 and 4 it will be complex. So we look at the literature. Also, I apologize, surely there are more articles related to the parabolic barrier and to the harmonic oscillator with negative mass. There are some recently works on Bose-Einstein condensation with system with which can be modeled by Hamiltonian with an effective negative mass. And we realize that the problem, we have realized of this a long time ago, but the problem to deal with the system in the non-PT symmetry phase is, of course, that the eigenfunctions are not square integrable. So it is, if we work in the Hilbert space, we have no spectrum. So we decided to work in the framework of Greek Hilbert space. Most of the audience, I am sure most of the audience are familiar and have worked with Greek Hilbert space, but let us give a brief resume. The Greek Hilbert space consists of a Hilbert space and two spaces that form the Gelfand triplet, a space which is dense in H, and a space formed by functionals acting on the functions of phi, such that the addition of f on phi is given by this bracket, and depending on the problem, the space phi is a compact space or a Schwarz space. Let us review the essentials of it. This is from a paper of Kruczynski, 1903. He worked with this Hamiltonian in terms of these two operators and construct the family of distributions associated to this problem. He introduced a distribution if 0 minus that obey this quantity, this condition, and a P0 plus that obey these conditions. Both distributions correspond to eigenvalues zeta over 2 times plus minus I, the imaginary constant unit, the imaginary unit. And then from them we can construct a family of distributions by applying m times b or n times u. And clearly these distributions are orthogonal, when one solves this equation, obviously, which the sense is the solving the equation in the sense of distributions. And the properties of orthogonality and closure are well known, and a function phi of the space D can be written in terms of these distributions. And moreover, there is also a continuous spectrum associated to the Hamiltonian I have proposed, and also the eigenfunctions of this associated to this continuous spectrum is well known in terms of distributions, and a function of phi can also be expressed in terms of these distributions. So let us come back to our problem. Let us come back to our original Hamiltonian, that is the Swanson model. The Hamiltonian of the Swanson model is this, and we can introduce a transformation, gauge transformation, and map the Hamiltonian H. Now H, we are thinking of H, and is adjoint as acting on the space phi times phi cross. We introduce two gauge transformations that the only difference between them is the interchange in alpha and beta, and we can map this Hamiltonian to this form, and we can make the same for the adjoint Hamiltonian. They look pretty much the same, but I will maintain the parallelism between them because I think it's more clear to show how to construct the orthogonality between distributions, the distribution associated to this problem and to this problem. Let us go back to region 2. M is positive and omega squared is negative. So omega can take values plus minus the imaginary unity and the modulus of omega. So that when I look at the parameter sigma, it has a phase that can take values plus minus p over 4. So we introduce a new set of coordinates and a new set of conjugate variables. We introduce u as y minus e py and b with the sign plus here. And for convenience, I will call overline u a u evaluated in minus gamma, and overline b a b evaluated in minus gamma. The complex conjugate of this variable is b, and the complex conjugate of this variable is u. So we end up with a Hamiltonian of this form, and similarly for the Hamiltonian of the adjoint of H. We can construct here also a set or a family of generalized eigenfunction or distributions in the same way that it was done in the work of Kruczynski. And we have for P over 4 these two sets of distributions. For P minus P over 4, this other set, and we work in the adjoint Hamiltonian, and we work with B instead of U, because from if we work in this way, it is clear that this set of distribution is orthogonal to this one. So we construct the orthogonality as usual with the eigenfunction of the adjoint and the eigenfunction of minus of the value with minus y is orthogonal to the eigenfunction with plus y. As usual, this happens also in discrete in the case of finite dimensional systems. These four sets are the same as this. I have constructed both here and here to look at this orthogonality relation. And then I can go back to the representation of y and p through these generated functions. We have these relations in terms of this generating function between the variables y and p and b and u, and we can construct the corresponding representation of the eigenfunctions in the whole set of variables by making this integral. I will not go into detail. In the paper we are writing, we add an appendix showing how we construct this integral and what is the path of the integral, and we use the fact that we can prove this. So finally, we end up for the region 2 with this type of discrete spectrum. We have resonant and anti-resonant states, and with this structure for the eigenfunctions. Concerning the continuous spectrum, we work as I have mentioned before, and the result are a family of eigenfunction related to the gamma function and to the parabolic cylinder functions. Again, we have an orthogonality relation and completeness relation. And what we can say at this moment is that the poles of this function is related to the poles of the gamma function, and the gamma function have poles for negative integral values of lambda, so that the poles of f are related with these resonant states and to the discrete function and to the function f plus m, when the poles of G are related with the anti-resonant states, so that when evolves in time, this will go as H. This should be the modulus of omega, m plus 1/2, while for this they will evolve as H minus H modulus omega m plus 1/2 t, so that we can, in some sense, split the phi space in functions. We can be represented by these functions, and functions that can be represented by this distribution in terms of these distributions, and some will evolve in this way and the others in this way, so that if we want to make the time evolution of the system for t greater than 0, we should take the advanced grid functions, while in the other case, the retarded grid functions. We have not advanced yet in the computation or the computation of mean values of observables as a function of time. We're just matching the eigenfunctions in each region of the model space parameter. In the region 3, we have m less than 0 and omega omega square, pardon, omega, yes, omega can take the value plus minus modulus of omega. Gamma takes values 0 or p over 2, so that here we have real spectrum, and the distributions associated to it can be obtained as before, and also related to a Hermite function, the Hermite function. There is a region in the parameter that is this line, where m have changed from positive to negative, and in this region we have found these solutions for the spectrum, while this region corresponds to value of the effective Victorian constant of the oscillator equals 0. So in this region we have the free particle motion simply. From we have learned until now, we think that perhaps in this region, in this border and in this border, we have exceptional points. We have not proved it. We guess that in this region we can have exceptional points also in this border. This line is quite difficult because m goes to increase very fastly to real values, positive real values in this sector and decreases in this other sector. So I don't really know if there is what should happen in the interface here. We have the solution of the equation, which we have derived. Here we have derived from the original Hamiltonian by taking omega equal alpha plus beta and taking alpha different of beta. Well, open questions, metric operators, exceptional points, and try to work on what happens with the time evolution of this system. Okay, to calculate probability functions, it should be not so difficult, but to take an operator x of p and make its evolution, it will take us a little more time. When we talk about time evolution, we refer to this operator. Sorry, I don't have to this operator. When we pretend to take mean values of these two operators. Well, and we have been doing in parallel is to work with a complex scaling method, this Hamiltonian, and we have some preliminary result. The complex scaling method is an approach to the treatment of resonances, and by doing a scaling, complex scaling transformation and fixing the scaling, we can construct sectors with square integrable functions and related the Hamiltonian or the mean values of the origin Hamiltonian to these related square integrable functions. But well, we have only preliminary result on this. Well, this is all we wanted to talk about today, and thank you very much for your attention.
Thank you very much.
Thanks, Marta.
Okay.
Any questions?
Yeah, there are several questions. May I ask them all?
Uwe, go ahead. Oh, go ahead.
Yeah, you have this usual Fock space representation, infinite dimensional. Do we have a clue when you are tending your parameters toward exceptional points, what's happening with these representations? In which way they are becoming singular? Probably you will have a horrible singularity there. How will it look like? How will it show up? Do we have an idea already?
No, we yet have not idea how they look. We know how is the function in the interface, but we have not yet analyzed the limiting process of the function in this section, in this sector, and in this sector.
Okay, so it's all these questions are still open.
Okay, we want to do this as the next step in this work.
I see. Okay, thank you very much. Very nice results. Okay, thank you.
More questions?
Hello, question here. Question?
Yeah,
Please,
go ahead.
can
Yep,
we go
can
to
hear
the
you.
first page? Can you get to the first page? Your first slide. Your first slide. Yes, no. Come again. Come again.
This?
Yes, yes, yes. Yes, no, no. The slide before, yes. Now, I want to ask, in what this algebra is Hopf algebra? For the
I
Hopf,
cannot hear well.
for the Hopf algebra, the slide on the Hopf
Yes,
algebra.
this.
Yes. In what this algebra is Hopf algebra?
I can't hear well.
I want to know what is in what this algebra is Hopf is for Hopf algebra.
It's a Hopf algebra because you can construct the co-product structure. Really, this is not a Kude form oscillator. This is a Hopf algebra in the sense of a Hopf algebra. You can construct the structure of co-product, the structure of I don't remember the name, but it's a Hopf algebra in the real sense. I can give you the reference where the people of Burgos have proved that it is a Hopf algebra, and they have constructed a co-product and everything, the antipode, everything.
Yes.
There is a reference of Ranz and Ballesteros.
Okay. Thank you. For the
I can
second,
send you
okay.
the references.
Okay, thank you. For the second question, please, can you come to the Hamiltonian that you want to construct a time evolution?
I really don't hear.
Yes, Hamiltonian that you showed in which you want to construct the time evolution. There is Hamiltonian which depend on his position dependent, something like that. I don't
Why
know.
we have choose this Hamiltonian?
Yes, how you construct his spectrum. I want to know how you construct his spectrum.
Okay, we proposed this Hamiltonian.
No,
We said, well,
no, there
if
is one for position dependent, phi of s, something like that.
why we have used this form?
No, there is Hamiltonian in your topic, which is depending on position, something like that. I don't know which slide is it. Come back again. Come down, please. Yes, come down. No, 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 come down again. Yeah, come down again. Yeah. No, no, no. Now, is no, 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 come down. Sorry for wasting the time. Come down again. Okay, maybe I can ask the question without wasting the time. I can ask the question or after line or offline.
This Hamiltonian.
Was it towards the end or more to the beginning, in the middle?
No, you mentioned when you are mentioning the open problem, the Hamiltonian that you have shown, which is phi of s, something like that.
This one?
No, you shown it when you are presenting your open problem. You come to an Hamiltonian that is position dependent.
But here is not more of algebra. Here is the Swanson Hamiltonian.
Okay, maybe without wasting the time, I will contact you offline.
Yeah, I think that's best. Yeah.
Okay.
Should we move on? Yeah. Maybe Philip, you're next. You have your hand up.
Yes, I wanted to just respond to Uwe's question a moment ago about what happens to the Fock algebra at the exceptional point. Carl and I explored that when we were looking at the Pi-Suhlenbeck oscillator. There are two frequencies, and when the two come equal, you go to an exceptional point. Now, if you just think of omega-1 minus omega-2 as some parameter epsilon, what we did is we redefined the Fock algebra before we took the limit, not afterwards. And we defined a new set of operators that did depend on epsilon, and then we were able to take the limit continuously. So if you want to do that, if you want to go from the non-exceptional to the exceptional Fock space, you've got to reconfigure the Fock space before you take the limit.
Yeah, so it's a kind of it's very sensitive to the in which way you are taking the limit.
No, we found one way that we could take the limit that wasn't singular, and I think it might. I mean, you certainly have to take a limit that's not. The whole point is, can you redefine the operators in such a way that you can find a limit that's not singular?
I see. Okay. Yeah, I see.
That's what we found.
Okay. And how are these different charts related? Do you remember this? You have different charts. In one chart, they're becoming singular. The other chart, they are staying regularly.
Okay. I'll read it to you. If you have operators A1 plus IA2, you replace them by A1 plus IA2 plus epsilon times A1 minus IA2.
Okay. Okay. Yes, I see.
It's a sort of Bogoliubov transform, but with a coefficient which itself depends on the parameter that's going to go to 0. And then you calculate. And the reason why this works is because when you get to the exceptional point, commutators become 0 because the Hamiltonian has 0 norm eigenstates. That's characteristic of a Jordan block Hamiltonian.
Yeah, sure.
And so the result is you want to find some combination that when you do let the parameter epsilon go to 0, you obtain not just a non-singular limit, you obtain commutators that then vanish.
Okay.
That's this is the paper we wrote in 2008.
Yeah, so, I remember your work, but I didn't remember this special point. Okay, I see. So I will check this your publication again. Thank you.
Actually, we wrote the FISREV letter on the unequal.
Yeah, sure. I remember. Yes.
And then we wrote a long paper on.
I know them both. Yes.
It's all buried in there. I'm sorry.
Yeah. No, okay. Thank you.
That's how it works.
Okay. Thank you also for the comment.
More questions? I just have a comment. Really, is less than a question. When you make alpha, beta, omega time dependent, then what we found is that the broken PT regime is restored, and the energies which now depend on time become real again. Yeah, so that's another way to go beyond the PT regime, to switch on time.
Okay.
Yeah.
Yes, I have to see the work.
Any other comments, questions? If not, let's thank Marta again. Very nice talk. Thank you. Very nice.
Thank you. Thank you, Marta.
Oh, thank you to you. Okay.
Please send us your slides. No?
Okay. I do it.